Okay, so it's iGCSE Physics, little introduction to Section 3B, wave properties. So we've got a lot of little terms here. So we've got degrees, so how we measure an angle, 360 degrees in a circle, same as 2 pi radians. Use that to measure angles from the normal from a surface to explain wave behaviors. So like when we're doing the law of reflection, you've got to measure it from there. So angle of incidence and the angle of reflection from there off a plane surface. So that's another part of the unit. We need to know about wavelength, symbol lambda, Greek letter, distance from a point on a wave is equivalent to a point on an adjacent wave, and wavelength is measured in meters normally. Could be kilometers, centimeters, but you have to convert to meters if you're using the wave equation. Amplitude of the wave, that is its maximum point. So if we look on this one, so from the middle of the wave here, it's how much it's going up by or how much it's going down. So it could be plus or minus A. Higher it is, the more energy it has. Now, frequency can be tricky. That's the number of complete waves passing a point in a second. So how many arrive per second? So of course, it's measured in hertz. A frequency of 5 hertz means there must be 5 complete waves passing a point in 1 second. Frequencies are given in often kilohertz or megahertz, and you've got some conversions to show you what it is. So like very straightforward. Time period is to complete 1 wavelength. So the time period is actually weird. It's the reciprocal or inverse of frequency. So if I know how many hertz it is, I do 1 over that and I get the time period. Frequency is the opposite. Frequency is 1 over the time period. So if it took a whole second for a wave to arrive, 1 over 1 is 1, frequency of 1 hertz. And then the last formula is the wave speed. Wave equation is frequency times wavelength, which is V is F lambda. Now for a normal mechanical wave, we use V. If it's an electromagnetic wave, we use C, which is the speed of light in a vacuum. Now then, a couple of other things. So we've got transverse. So the wave might be traveling from left to right, but the vibration of the particles, or it could be the electromagnetic wave, is also transverse, is from side to side at right angles or 90 degrees to the direction of travel and energy propagation. Longitudinal, a slinky can show it quite well by actually the springs coming closer together and further apart. So we get compression and rarefaction. One compression to the next compression is equivalent to the wavelength in this case. You can see here the wavelength. So particles are moving parallel to the direction of the wave travel. Refraction, so waves will slow down or bend towards the normal as they enter a prism like this. So there's glass and here's air, and the wavelength becomes shorter. So velocity slows down, frequency is a constant, so no color change, but the wavelength will go down as well. So wavelength is proportional to V. Waves will speed up when they exit the less dense medium and they will bend away from the normal, which you can see here. And you've got incident and refracted angles, and then refracted and incident angles. Again, effectively, I've put the I there, though it's the R one, but they are the same. That one at the top is the same as that one at the bottom, and that one here is the same as this one here. And you also might get a weakly reflected ray as well, because it will obey the law of reflection. So that's your basic wave properties.